Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In the previous video, we were dealing about preparation and properties of alkanes which fell into the category of saturated hydrocarbons. In this video, we will be taking up alkenes, which is the first member of unsaturated hydrocarbons, which is a part of hydrocarbons only. So unsaturated hydrocarbons means there is the presence of double as well as triple bonds, and alkenes fall under those category which have the presence of double bonds in their structure. Okay, so first we will take up the preparation of alkenes. The first preparation is alkyl halides. Okay, that is from RX. This is a process, this process is called as by dehydrohalogenation. Now, what do you mean by dehydrohalogenation? The removal of hydrogen as well as the halogen group HX. Okay, basically the removal of the removal of HX. Now, how can it be removed? See, let's say for example the structure is CH3, CH2, Cl. Okay. Now, if I am removing one hydrogen from this carbon and the halogen from this carbon, then there will be a development of a double bond between these two carbons, which will ultimately result in the formation of an alkene, right? And this is called beta elimination. What do you mean by beta elimination? See, to this carbon, the halogen group was attached, right? So this carbon was called as alpha carbon, or the carbon to which the functional group is attached, that carbon is called the alpha carbon. So now here what happens? To the alpha carbon, the next carbon that is attached is known as beta carbon. Now, if there is removal of hydrogen from this beta carbon, then this process is known as beta elimination, that is elimination of hydrogen from the beta carbon. So here what happens, if they are reacted with alcoholic KOH, when any alkyl halide is reacted with alcoholic KOH, then alcoholic KOH leads to elimination reaction. You have to remember, alcoholic KOH leads to elimination reaction. Here elimination of what? Elimination of a hydrogen and a halogen group. So here what happens? Suppose KOH was there, it broke down to K plus and OH minus. Now here OH minus acts as a base, and the work of a base is to extract a proton, right? So what happens basically, this OH minus extracted a proton from this carbon atom. Now this what happens, see, let me show you the exact mechanism here, how the reaction has proceeded. Suppose I am saying CH2, H was there, basically CH3, and it was attached to CH2X. When OH minus attacked this species, it basically extracted a proton from here. Now this bond shifted onto this carbon atom, and this led to the elimination of X minus. X minus, when it got eliminated, in its vicinity there was presence of K plus ions, which K plus ions was coming from this KOH, K plus and OH minus. Now this K plus combined with this X minus to form KX. Here as the X was bromine, so it is KBr, and this OH minus took up an H plus to get removed as water, H2O. This led to the formation of ethene, a double bond between these two carbon atoms. This is the mechanism how this reaction actually proceeds. Now if I see here propyl bromide to this is the alpha carbon, and here this is the beta carbon. When it reacts with KOH, again beta elimination takes place. Beta elimination results in the formation of propene, KBr and H2O. Okay. Now in case of unsymmetrical, here the alkene was symmetrical. That means if this is the alpha carbon, then there is only one beta carbon possible for this. Therefore, elimination has to take place from beta carbon. It has no other option. Therefore, this reaction, whatever that has happened because there is only one beta carbon position possible. But if suppose I am saying the structure is somewhat like this. Now the problem arises, for this carbon to be alpha, it has two beta positions, one on the left, one on the right. Then in that case, what happens, from where the hydrogen will be removed? Now if I see this example, then both the positions are equivalent to me. But imagine if I am associating another CH3 on this side and this remains as CH3 only. then the problem arises because there are two different kind of beta carbon associated. To one beta carbon there is a presence of another CH3 group, but to this beta carbon there is no such alkyl group associated. Now we get two different kind of environment on both the sides of the alpha carbon. Then in that case we follow a rule called as Markovnikov's as well as anti-Markovnikov's rule, basically in case of unsymmetrical alkene, and that's where questions come from. Okay, symmetrical nobody is going to ask, this is for your understanding only, but questions usually come from this unsymmetrical part. So what happens in case of unsymmetrical alkyl halide that has two beta carbon possible, then there is, suppose I'm saying this example, this bromine is by default going to get removed, but if suppose this hydrogen is getting removed, then I'll get the product as but2ene. Now if this hydrogen is getting removed, I'm getting butene only, but1ene. Two different products. Now which one will be the major product, which product will dominate, and which will be the minor product? That is defined by a set of rules. So the first, in this case, it has two beta carbon. So we make use of a special rule called Sedzev's rule. Okay. In case of Sedzev's rule, it says in case of reacting alcoholic KOH with unsymmetrical alkyl halide, that alkene is preferred which is alkylated, maximum alkylated, or which is bulky. Okay, I'm sorry, Markovnikov's and anti-Markovnikov is followed during addition. In elimination, Sedzev's rule is followed. So here what happens in case of reacting alcoholic KOH with unsymmetrical alkyl halide, that alkene is preferred which is maximum alkylated, basically the bulkier one. Okay, so in case in the both the like examples, but2ene is preferred. Why? See, if I'm seeing this carbon, it is maximum alkylated because it has a CH3 group associated to linger the chain. But here only one CH3 and this is the terminal carbon. So basically terminal alkenes are not preferred. Okay, this butene is a minor product, but2ene is the major product, and this is as per Sedzev's rule. Okay, so if we see the elimination order, then always remember iodine is the best leaving group. Iodine tries to leave the compound very easily. So if I see the order, it will be iodine which is highest, followed by bromine, chlorine and fluorine. Fluorine being smaller in size and highest in electronegativity, this is the least interested in leaving the molecule or leaving the electron vicinity. Okay, the better the leaving group, more easily the reaction occurs. Now if I see the reactivity of alkanes towards this reaction, then it will be tertiary, which is highly reactive, then secondary and followed by primary. Primary alkyl halide is least reactive to such kind of reactions. Now from dihalogen derivatives, if I see we have two types of dihalides. One is vicinal halide, vis dihalide, and the one is geminal or gem dihalide. Now see, if I'm saying whatever be the chain, to one particular carbon atom both the halogen groups are attached like this, then this is the geminal dihalide. Dihalide means two halide groups. Now if both the halide groups are attached to the same carbon atom, they fall under the category of geminal dihalide, and if both the halogen atoms are present over different carbon atoms, they form under the category of vicinal dihalides. Now, to removal of vicinal dihalide results in the formation of an alkene. For example, if I am saying CH2 to it, two bromines are attached, that means 1,2-dibromoethane, that when reacts with zinc, then it forms ZnBr2 followed by the generation of a alkene which is ethene. Okay. In this, renewal of halogen is taking place, removal actually, not renewal. Removal of halogen is taking place, therefore the process is called dehalogenation. D means removal, halogen group is getting removed, that's why dehalogenation. Okay. Next is from alkynes. Now alkynes will lead to alkene if there is addition of hydrogen to that. So in this process, again, hydrogenation takes place. Remember the case of alkanes. To alkene, if I'm hydrogenating, I'm getting a alkane. If I'm hydrogenating alkyne, I will get the next member, that is alkene. Okay. The reaction involved is, if ethine is combining with same hydrogen in the presence of nickel metal, it is giving rise to ethene. Okay. Now if this again this CH3 C double bond C CH3, it is reacting with H2 in the presence of, remember, Lindlar's catalyst or Lindlar's reagent. This is called Lindlar's reagent, which is basically palladium and barium sulfate, PdBaSO4. Okay, Lindlar's catalyst is, or Lindlar's reagent is PdBaSO4. Now, if this particular alkene is getting associated or reacting in the presence of PdBaSO4, then what happens? Obviously, as we are studying it under hydrogenation, then obviously there will be addition of hydrogen. But there are two possibilities. One is both the hydrogen can get attached on this side, or one can get attached on this side and other can get attached on the opposite side. So if both the hydrogens are getting attached in the, like, you would think that how would it even make a difference, right? No, the difference is in stereochemistry, that is three-dimensional arrangement around the atom. Now if I see, I am just showing you in a 2D scenario, right? But actually this is three-dimensionally present. Why? This is an alkene. That means that the presence of pi bond above and below the plane means it no more remains a planar structure. It goes into a three-dimensional structure, right? So although on pen and paper it would not make any difference wherever you get attached the hydrogen, but if you see practically in a three-dimensional orientation, it would actually make a difference. Okay, so if the hydrogen is getting attached to both the carbons on the same side, then it forms a cis isomer. If it is getting attached on opposite sides, it is leading to the formation of a trans isomer. Okay, so if the alkene is reacting with hydrogen in the presence of Lindlar's catalyst, which is palladium barium sulfate, PdBaSO4, then the isomer formed will be cis. Addition of hydrogen will be on the same side of alkene. Okay, and if it is reacting in the presence of, like, this particular reaction is getting carried out, this particular reaction is carried out in the presence of sodium metal. This is called Birch reduction, sodium and ammonia, NaNH2. Okay, sodium amide, NaNH2. Then this reaction results in the formation of a trans isomer. If it is in the presence of PdBaSO4, it will form cis. If it is in the presence of NaNH2, then addition of hydrogen will no doubt occur, but trans to the alkene, like the trans to the original position. And this particular reaction, the trans addition, has got a special name called as Birch reduction. BIRCH, Birch reduction. Okay. Now if I see the next method, which is from alcohol, again if I am seeing alcohol OH, there is one H in the vicinity, so I can see chances of removal of water, right? If I am removing water from this molecule, if I am getting, or if I am doing dehydration, then what happens? I have some chances of forming alkene, right? So see what happens. If to this ethanol CH3, I am adding concentrated H2SO4. H2SO4 is a strong dehydrating agent. Okay, it's an acid obviously, but it is a strong dehydrating agent. So what happens when I'm subjecting this ethanol to concentrated H2SO4? There is removal of a molecule of water, basically this OH and one hydrogen from somewhere on this carbon, this getting liberated as water, and I'm getting my ethene or the desired alkene. Okay, now the ease of reduction is obviously 3 degree greater than 2 degree greater than 1 degree. Okay, 3 degree alcohol is more reactive to formation of alkene than 2 degree. Next, so least reactive is 1 degree. Now if I see the physical properties of alkene, again existence, the lower members are colorless, ethene is sweet in smell, and other alkenes are odorless. See, ethene here is the starting member. In case of alkane, methane was the starting member. But here, double bond is possible only when there are two carbon atoms, because double bond between what? Carbon atoms, right? So it takes two carbon atoms to form a double bond. So here the starting member is ethene. And then if I see at the melting point, alkenes have higher melting point than alkanes because pi electron cloud will be more polarized. Although not much, but certain degree of polarization starts developing from alkenes itself. Okay. If we compare melting point of cis and trans, then trans possesses higher melting point than cis. Okay, why? Because trans have a symmetrical structure. Trans, again remember, melting point is entirely based upon symmetry. Now trans being more symmetrical, they fit into the crystal lattice properly, therefore they will have a higher melting point than the cis isomer. Now next is boiling point. They show like regular graduation with increase in carbon atom, van der Waals force increases, so boiling point increases. Boiling point decreases with increase in branching. Why? Surface area decreases. As surface area reduces, van der Waals force decreases, therefore boiling point also decreases. Now out of cis and trans if I see, then trans has lower boiling point and cis has higher boiling point due to polarity factor. Okay, trans is less polar. Why? See, suppose I am saying double bond. Let me say here Cl is there, here Cl is there, this is trans isomer, right? So the the dipole moment will be directed this towards this chlorine and here it will be directed towards this chlorine. Now see, these both are antagonistic to each other, alright? Therefore, this will cancel out the dipole moment created by the other carbon chlorine bond. Here the net dipole moment reduces. But if I see the on the same side, if I see cis structure, then what happens? The dipole moment has a net value downwards. Okay, the dipole moment is not getting cancelled out here, as a result of which this is more polar than the trans isomer. So if I see the boiling point, out of cis and trans has a lower boiling point and cis has higher boiling point due to some polar character in cis isomers. Now if I see solubility, alkenes have greater solubility than alkane because again here a certain degree of polarity arises due to the pi electron clouds. So lower members are sparingly soluble, but as the members increases, the polarity value increases, but they become gradually they are more soluble. Lower members are less sparingly soluble, but soluble in organic solvents like benzene, ether, carbon, tetrachloride, etc. So those insoluble in water will be highly soluble in non-polar solvents. Okay. Now if I look at the chemical properties, obviously as compared to alkanes, alkenes will be highly reactive. So chemical properties of alkenes, it shows mainly two types of reaction. One is electrophilic addition and the next is oxidation. Electrophilic addition. What do you mean by electrophile? Phile means loving. Electro means electron. So electron loving species are called as electrophiles. Now electron is in itself negatively charged. So for a species to be electron loving, that must be oppositely charged. That means it has to be positive charge. So therefore, if to an alkene there is addition of any E plus charge groups, electropositive group, okay, they come under the category of electrophilic addition. Now if I see the general reaction, this is an alkene. To it, suppose I am adding anything AB, where A is positively charged and B is negatively charged, then what happens? See, there is alkene. So by default, this charge, the negative charge, is not uniformly distributed. One among them, suppose let's say this carbon atom is having a delta negative charge, this carbon atom will have a delta positive charge. When this A positive is going to come and attack on the negative side, or this negative charge will attack this A positive, then there will be development of a Ca bond, the double bond will break, and as the negative part of the addendum has gotten attached to the A plus, so this carbon will be left behind with a positive charge, basically generation of a carbocation. Now to this carbocation what happens? Any negative part will come and attack. Okay, so if this is the intermediate, carbon is having a positive charge, then the B negative is coming and attacking on the positive side. to develop or to form this compound. Basically, there is an addition of one bond has broken down and there is addition of a molecule A, B. Now, primarily, first of all, what has happened? B plus, okay, or the electrophile has come and attacked itself on the, or the alkene has gone and attacked the B positive charge. Therefore, there is addition of an electrophile. Therefore, this reaction is primarily falling under the category of electrophilic addition. The more the ease of reaction, more stable is the intermediate, which is the carbocation. Now, the ease of reaction will be depending upon the stability of carbocation. Got it? Now, if I see addition of halogen. Okay, another thing, if I am seeing this, then of course, if there is any chances of formation of 3-degree carbocation, then that reaction will be more feasible because carbocation stability was in the order 3 degree greater than 2 degree followed by 1 degree. So, if there is a generation of a 3-degree carbocation, then that will be highly reactive to this reaction followed by 2 degree and lastly 1 degree. 1 degree primary thing will be very least reactive to this kind of reactions. Okay. Now, if I see addition of halogen, then obviously halogen, it can be fluorine, chlorine, bromine or iodine. Now, if I am seeing ethene reacting with bromine in the presence of CCl4, carbon tetrachloride, basically a non-polar solvent, then in that case what happens? There is generation of 1,2-dibromoethene. Remember, in one of the preparation, from 1,2-dibromoethene we have prepared ethene. Now, from ethene we are again adding Br2 to result in the formation of 1,2-dibromoethene. And if from 1,2-dibromo I was forming ethene, then that reaction was called as dehalogenation reaction, removal of halogen group. Order of reactivity: fluorine, chlorine, bromine and iodine. In case of addition of fluorine, the reaction occurs so violently that it leads to explosion, and it is a very highly exothermic reaction, and it is so fast and so like explosive that we rarely or hardly get to witness the reaction actually happening. Okay, and in case of iodine, the reaction is taking place under very special condition because iodine undergoes rampant oxidation. Okay, so the condition is highly reversible. So this reaction is also considered as a test for unsaturation. Like if we need to see whether the compound is a saturated compound or an unsaturated compound, we react it with halogen and mostly bromine water. Bromine water, like the test for unsaturation is the decolorization of bromine water. If bromine water loses its color, that means the bromine bond has broken down and bromine has attached itself to the unsaturated site or the unsaturated part of the hydrocarbon, then that's when the bromine water loses its color, right? So, if bromine water is getting decolorized, then that hydrocarbon was a unsaturated hydrocarbon, and that particular test is called bromine water test. Okay. So, if I see bromine water was having a dark brown color. If the decolorization occurs or if it turns colorless, then there is obviously the presence of a unsaturation in that hydrocarbon. Next is addition of halogen acids. The order of reactivity usually follows is, if addition has to take place, then Hi will have the highest tendency of getting added, followed by HBr, then HCl and HF. Why? Because HF, fluorine, is very small in size and is highly electronegative, and fluorine forms hydrogen bond in between its own molecules. As a result of this hydrogen bonding and electronegativity, it is very difficult to break HF into its respective ions. Therefore, addition is very slow in case of HF. However, iodine, as I said, is a good leaving group. It can easily leave its hydrogen counterpart and form I- ions. Therefore, it undergoes ready addition to the alkene. Okay. So, if I see this, the Hi has weak bond because of incomparable size. That is the reason of its high reactivity towards the reaction. So, what happens? Alkene, HBr, the bromine is getting added to the hydrogen is getting added to the negative counterpart and bromine is getting added to the positive counterpart, and we get bromoalkane. Okay. Now, in the what discrepancy arises if there is a unsymmetrical alkene. If unsymmetrical alkene is there, then usually Markovnikov's rule is followed. Now, what does Markovnikov rule states? See, Markovnikov rule says that addition of any group of unsymmetrical alkene, the negative part of the reagent will attach itself to that carbon atom which carries lesser number of hydrogen. That means higher, bulkier, like the bulkier carbon atom which is getting attached to more number of carbon atoms, or where there is greater branching arises, or branching, or there is association of other carbon atoms, basically the bulkier carbon site. Okay. So the negative part of the addendum will go to that carbon atom which has lesser number of hydrogen or more number of substitutions or more number of carbon atoms. So the carbon atom carrying lesser number of hydrogen, and the hydrogen goes to the carbon atom carrying maximum number of hydrogen. Okay. So if I am saying HCl, that will break into H plus and Cl minus, and Cl minus will go to that carbon atom which has lesser number of hydrogens. But if I am taking any, in presence of the whatever substrate I am taking, with that I am taking hydrogen peroxide. In the presence of peroxide, the rule gets reversed. That means the negative part will get attached to that carbon atom which has higher number of hydrogen atom, and this is antagonistic or opposite to the Markovnikov's rule. Therefore, it's called as anti-Markovnikov's rule or peroxide effect, or basically Kharash effect, and this effect is mostly observed in only for HBr. Okay. Only for in addition of HBr, the anti-Markovnikov rule is followed. Okay. Wherever you see the peroxide presence, benzoyl peroxide, it will obviously follow the anti-Markovnikov rule. Now see, Markovnikov rule is for all attacking reagents, but anti-Markovnikov rule is only followed for HBr due to thermodynamic reasons. Okay, for HCl, HI and all, anti-Markovnikov rule cannot be followed. Now, the another thing is, first of all, what was happening, like we are taking any HCl or HF or any HX we were taking, any halide, halogen acids we were taking, it was breaking down into H plus and X minus. The H plus was getting attached to the negative part of the alkene. There was resulting in it was resulting in the formation of a carbocation. Now we have said that the order of, or the stability of carbocation follows the order 3 degree greater than 2 degree greater than 1 degree, right? So after the addition of hydrogen, we were forming a hydrocarbon, we were getting a carbocation. Now if there is any scope that by transfer of a CH3 group or a hydrogen group, like basically a methyl shift or a hydride shift, that particular compound can lead to a stabler hydrocarbon, then that compound will without any hesitation go for that path. Like for example, if I am seeing here, it is breaking down into, this double bond was breaking down, this H plus was getting attached to the more number of hydrogen atoms, basically following Markovnikov's rule. So it was becoming CH3 and CH plus. Now if I see here, this CH plus is a 2 degree carbocation, but if I shift this hydrogen atom onto this carbon, then here there will be a resulting carbocation, and now this carbocation will be of the order 3rd degree, right, which is more stable than 2 degree. So if this atom is seeing, if I am taking up one H plus from the nearby atom or the nearby carbon atom, then that carbon atom is leading to a 3 degree carbocation, like more stabler than me. So as a result of which what will happen, without any hesitation there will be hydrogen shift, and the shifting can be either of a hydrogen molecule. If there was probability of CH3 shifting also, then that will also happen. Mostly hydride shift and methyl shift. Now here there is a methyl group, there is a hydrogen group, but a hydride group, but as there is presence of a less bulkier group, hydride group, it can easily migrate. But if there is some other group which is more bulkier than the CH3, then in that case, the CH3 being the less bulkier group, that would have shifted, right? So there is a shift of H plus to this carbon, and there is resulting 3 degree carbocation, which is maximum stable. Okay. Now the next reaction of alkene is oxidation with ozone. Now it is called ozonolysis. Ozone, O3. So basically what happens when it is reacting with ozone, 3 molecules of ozone are getting added to form a ozonoid. Okay, and in that ozonoid, when it reacts with water, it undergoes hydrolysis to form an aldehyde and hydrogen peroxide. Okay, 2 molecules of methanol are formed with a liberation of hydrogen peroxide. So this was the oxidation reaction with ozone. So that's it for alkenes. Here we have dealt with preparation and physical as well as chemical properties of alkenes. In the next lecture, we'll be taking up alkyne. I hope you are clear with this chapter. Thank you so much.